Hello everyone, so we are now into section 5.8, which is on ropes and pulleys, and you'll see this quite a lot in the near future. And so basically whenever we're talking about ropes and pulleys, the force that we're going to be talking about is, of course, tension. Okay, whenever you have ropes, cables, strings, etc., we're talking about the tension force. Okay, and if you're not sure what a pulley is, I'll point it out in a picture on the next couple pages here. And there's a few really key points here for this class. So we're making a lot of assumptions here. Okay, the first one is that the rope / cable or whatever is massless. Okay, in general, string has a very, very small amount of mass. So we're going to make that assumption. We're also going to make the assumption that pulley is massless for right now. Okay, and we're also going to consider that the pulley is frictionless. Okay, so oftentimes in this class we assume kind of like an ideal case. Okay, so the pulley is frictionless here. Okay. Alright, also the tension is the same throughout the entire rope. Okay, so it doesn't matter if it's towards the base of the rope or in the middle, the tension is the same. Okay, so let's go to the next page. Alright. I should have maybe made this 2 pictures. Okay, so this is what I was talking about here with the massless string approximation. Right here. So there's no weight force on the string or rope here. Okay. So sorry, from the previous picture here, what you'll kind of see is if a rope is attached to a box, if we consider the forces on the box, we have that tension force, of course, which is right here. If we consider the forces on the rope, we have the force, the reaction, essentially the reaction force of the box on the rope, and then we would have another force, which in this case would be the applied force here, or F. Okay, so what we'll see is that the forces on the rope will basically cancel out. So we're only going to be drawing free body diagrams for the objects that the ropes are attached to. Shoot. Okay. Okay. So this is what I was saying here. The tension is equal to the tension in the rope is equal to the tension in the rope throughout the entire rope or cable here. Okay. So there's an example that you guys can look at. Now with pulleys, this is kind of going to be a really similar, a very common situation that we'll see. If you're not sure what a pulley is, that's what this is right here. So it has a circular kind of wheel, basically, that the rope goes through, which is going to allow this pulley to spin. Okay. Now this example here on the bottom left is a type of Atwood machine, and this is going to be the majority of the questions that you will see. Okay. So like I said, we are considering the pulleys to be massless and frictionless as well. Okay, but if we're looking at this example here at 5.32, the tension here and the tension here are the same. And that should make a lot of sense to you because it is the same rope. Okay. Also, if, let's say, box B accelerates downwards, that means box A will accelerate to the right. Okay, they are attached to each other. So just like in 5.7, when looking at interacting objects, A and B here are physically attached to each other with this rope. So even though it's going through a pulley, they are still connected to each other. So whatever acceleration B experiences, A will also experience. Okay, it's a really, really key point there. So let's go to our first example here, and we'll kind of look at our information. And this is basically going to be a simple Atwood machine example. Okay, there's a better picture on the next slide. So we're given the mass of this set is 200 kilograms, and it is stored above the stage. The rope is going through a pulley. The director tells a 100 kilogram stagehand, so a person, to lower the set. When he unties the rope, the set falls, and the unfortunate man is hoisted into the loft. What is the stagehand's acceleration? Okay, so basically, we'll see the nice picture on the next page, but basically we have this 200 kilogram set and this 100 kilogram person, which I don't feel like drawing. So basically we have 200 kilograms on the right side and 100 kilograms on the left side. Your intuition should tell you that it is easily going to rotate this way, which is going to cause this to accelerate downwards, which means this is going to accelerate upwards. Okay, so this is maybe the only time where this can get a little tricky is remember that this is accelerating downwards and this is accelerating upwards. The magnitude of those two accelerations will be the same, but they're just in opposite directions. So I'm going to be consistent throughout the entire year and use a negative value for down and a positive value for upwards. Okay, so to be consistent with their notation here, M is representing the person, so that is the 100 kilogram person, and S is the set. Okay, so looking at the forces here for the person. Okay, so for M, our free body diagram is pretty simple. We have a large tension force and a relative small mass. Okay, so my Net force in the y direction will be here. So we have tension minus the weight is equal to the mass of the person times the y acceleration. Okay. On the next page, here, for the set, the forces are really similar. So for the set, instead, it's going to be accelerating downwards. So we have ms, g, and then we have kind of a smaller tension force. It's the same magnitude as the other one. I'm just kind of bad at doing this on small screens. Okay, so it's the exact same tension force that is acting on the person. Okay. So you'll see that we have two equations for tension. Okay, so we have one in terms of the man here on the top, and then on the bottom we have one in terms of the set. Okay. Okay, so what we're going to do is we're going to use our top equation to solve for tension. So literally all they do from here to here is that they add the mass of the man times g, so its weight, to the right hand side. So this is just an example of substitution. So this right here is going to be inputted to there for t. Okay, so if you can see this, all this is t. This is t. And then we set this equal to, and remember that I told you that acceleration is negative because it's downwards. That's why it is minus msay. They basically just distributed the minus sign. Okay. So what you'll see now is basically you're going to be solving for acceleration. So acceleration is on both sides here. Okay, so I'm going to show this intermediate step down here. Okay, so basically we have mm, and I'm just going to say it's ay because there's no point in giving subscripts to it because it's the same value. And then ms ay, so I'm adding this to the right hand side, and then I'm basically going to move the others to the other side. ms g minus mmg. Okay, so now we can just pull this out. mm plus ms, and then we have g ms minus mm. Okay, now you'll see this question or this expression very, very commonly. If we solve for acceleration, we will get this. Okay, so the way I had mine written, acceleration is still, or g is still in the numerator, but we'll see it is essentially the difference in the mass over the sum of the masses times g. So the acceleration that we're going to have downwards here and upwards here is going to have a magnitude of 3.3 meters per second squared. So downwards for the set at 3.3 meters per second squared, and upwards for the person at 3.3 meters per second squared. Okay. Okay. So I wanted to do another example. So I wanted to do number 83. I would recommend trying to do 82 and 84. But this is a really good question here. So because it involves your favorite things, it involves a rope pulley and now a ramp. Okay, so this is still kind of like an Atwood machine. Atwood machine is like a general description for two objects connected to each other with one rope going through a pulley. Okay, if the blocks are released from rest, so if they're released from rest, that means basically your hand would be keeping them stationary. So whenever you release it, it's going to accelerate one way or the other. Okay, so let's make sure we read this correctly. This is not in equilibrium. And I think a clever reader should be able to notice that because it says which way will it move. Okay. All right. So to be consistent here, I'm going to label this 1 and this 2. So the very first thing I want to do is draw my free body diagrams. So for block 1, block 1, okay, we have the upward tension force, which I'm just going to call T. Then we have the normal force, which is going to be like this. Then have mg. Okay, and I should be maybe a little bit better here about it, because this is a bit longer, because it's 10 kilograms instead of 5. Okay. My second free body diagram is much simpler. It is tension, straight upwards, and then M2G. And it's a little bit hard to draw your arrows here, your vector arrows, with this type of question because we are unsure about what direction that the acceleration will be. So at this step, don't worry about it. Okay, so I'm going to do my forces for 1 first. Let's do the X. Okay, now we've done this sometime here. So remember that this is the X direction. This is the Y direction. Okay, so I know I've done this many, many times, I feel like, but I will do it again. Okay, so this point right here is mg cosine theta, and this part is mg sine theta. Okay, if you draw it like this, the angle is right here. Okay, remember you could draw it this way instead. Does not matter. It only changes where the angle is. Okay, you guys should know from geometry that these two angles would be equal to each other. So whichever one suits your fancy is what I'm going to say. Okay. All right. So to the right, in the positive direction, I have tension. In the negative direction, I have the x component of my weight force. So this m1 g sine theta, which the angle is 40 degrees. And this is, it's going to be accelerating. I just don't know what direction right now. Okay, and in the y direction, which is kind of not important, but we'll draw it anyway, is the normal force minus mg cosine theta. And we should not have any acceleration in the y direction. Okay, so no perpendicular acceleration to the ramp. Okay, for this, luckily we only have one free body diagram to do. And this is just t minus m2g, and that's equal to m2 times ay. Okay, now even though the accelerations are in different directions, as far as one is in x, one is in y, ax in this case will equal ay. It's the same because they are connected to each other by a rope. Okay, now at this point you can really make your own judgment or your own decision here, but we're going to have to do a substitution, and that's because there's a lot of things that we're going to have two unknowns really in any equation that we do here for box 1 or box 2, except for the y one for box 1, which is not going to help us at any shape or form because there's no friction. Okay, normal force is usually really helpful for friction. So you could do it the other way, but I'm going to say, okay, so tension is m2ay plus m2g. And I'm going to put this substitution essentially right here. Okay, so I'm going to do that on the next slide. So that gives me, let's see, m2ay plus m2g minus m1g sine theta equals m1 ax. Okay, so it doesn't matter that one is ax, one is ay, because they are attached to each other, they're going to be the same. So what I want to do, the only way I can solve for this is if I get those two accelerations on the same side. Okay, so I'm going to do m1 ax minus m2 ay. This is equal to m2g minus m1g sine of theta. Okay, so my right hand side I'll be able to pull out, and I'm just going to call it a since it's in both directions, m1 minus m2, and over here I could pull out g if that makes you guys feel more satisfied. m2 minus m1 sine theta. Okay, so the acceleration will be g m2 minus m1 sine of theta over m1 minus m2. Okay, so slightly different. Remember in the other one we had the addition of those two on the bottom. So of course I make mistakes too, and so let's look at this. So it's frictionless. So you should, if you're looking at this, if there's no friction from this ramp, you should think that it's going to move and accelerate this way, which means this is going to accelerate upwards. Okay, so I should have actually made a change here. So that means that this would be negative because it's going to be going down the ramp. This will stay positive, so I'm fine there. But what that changes is this right here. That's going to be negative, which means this is negative, which means right here, if I pull out the negative, this should be And so you could write it this way, or you could write it as m2ay minus m1ax. Same thing here. Okay, or actually it'll end up being plus because we're going to be adding it to this side. Okay, so yeah, let's go with it that way. Okay, so m2ay plus m1ax. The left-hand side is still the same, it's still correct. Basically, that's going to change this to be positive, and this to be positive. Okay, so the acceleration, 9.8 meters per second squared. M2 is 5 kilograms minus M1 times the sine of, which is equal to about 6.4 to round a little bit. And this is going to be over 15 kilograms. You should get it about negative 0.93 meters per second squared. Okay, so you can learn from my mistake in a situation like this. So in a lot of cases, if they're giving you something that involves kind of two complex movements, usually friction will be ignored, at least at this point. So your intuition should tell you that it should go left there. Okay. Alright, so you definitely want to try something like 82 and something like 84. But this is the main concept of pulleys and ropes. And usually they're connected to each other. So we have interacting objects and tension and pulleys working together. So basically draw a free body diagram for each object. And remember the acceleration is the same, but the acceleration can be positive for one and negative for the other, depending on the direction of its acceleration. Okay? All right, good luck.